Hello, and welcome to this installment of our video series with ASCO. I am Amara Rozgis with Consulting Specifying Engineer, and I'm happy to be here with you today to discuss a variety of power and energy-related topics. Today, I'm speaking with Russell Senesac, who began his career with APC in 1996 and has held several positions in the past 25 years, including sales, product management, and strategy. His concentration has traditionally been in mission-critical applications, specifically within the data center and edge environments. Within Schneider Electric, Russell has most recently been focused on market trends, disruptions, and collaborating with R&D teams to solve the challenges faced by partners and end-user communities. Just recently, Russell broadened his focus to include the rapidly developing new energy landscape, which includes electrical source management, distribution, and load prioritization. Hi, Russell. Thanks for joining us.
Hey, Mara, how are you?
Very good. Thank you so much. So we've talked about a lot here, but now let's put it all into practice. So from an industry standpoint, let's understand the where and how of a source isolation switch. Let's understand how it would be deployed.
Yep.
So can you get us started on some basic use cases or some examples?
Yeah. No, we're going to spend a little bit of time today on those use cases because these really kind of put to music, I think, some of the podcasts that we've been covering over the last couple of weeks here, because source isolation switches, as we talked about, you use them differently than you do transfer switches, right? So we talked about how transfer switches to a generator as an isolation switches to a battery. We talked about how generators and transfer switches do exactly that. They transfer, right? Now we're going to talk about how if you're using batteries with isolation switches, they isolate. And so I think doing these use cases will be very effective in helping folks understand, how do I actually use one of these in practice, or where should I look for one in my overall design itself? So the first use case that I wanted to spend some time on here is what I would call the battery only use case. So in this scenario, I've got utility and I have my distributed energy resources, right? Those are those DERs. So this is, remember in one of our podcasts, we talked about majority of the time, you're going to have a solar system with a connected battery energy storage. So we kind of put that in a bucket, call that a DER, a distributed energy resource. So that DER has an inverter that is typically either two of them or they're coupled together for one of them. It just depends on the plumbing over there. But usually there's an inverter over there that's connected in normal grid tie mode. So this green line that you now see here, that's powering your standard loads and your essential loads. The idea here now is utility is providing power, and the energy storage system, the battery itself, and the inverter is connected directly to the utility. And so now you can see that SIS that you've now placed between your essential loads and the utility itself. So the idea is that not all loads within your building are created equal, right? There's going to be things that you're going to look at that you're going to say, those are critical, that if the power goes out, I want to be able to provide some level of resiliency. And then there's going to be the stuff that you're going to look at and say, it's okay if the cafeteria lights go out because nobody's eating or anything like that. So that's going to be critical, is where you're going to choose to place it. But what we're going to walk through here now is going to be that sequencing that's going to happen is what happens when the power actually goes out. So if we go to the next step in terms of how this is going to build, what you're going to see now is that I've lost power. And that's the black line. The isolation switch is signaling the inverter itself to be able to provide power. So the first thing that happened is that switch opened and created that isolation, sent the signal over to the inverter, said, hey, I'm isolated, it's time for you to make some power. The inverter said, great, I'm isolated, I'm going to make some power. And that's that blue line that you now see that's powering the essential load. So now what's going to happen is the utility is going to come back. And once that utility comes back, that isolation switch is going to say, hey, I see that utility came back, and I'm now going to signal over to the inverter to say, hey, you need to stop creating power, and now you need to go back to a grid following mode. So if we take that next step, you're going to see that green line come back. So here it comes. Isolation switch says, hey, power's back. I'm sending that signal over to the inverter. The inverter says, hey, got the signal. I'm going to stop making power. An isolation switch says, great, I'm now going to reconnect us to the utility. And now the utility is powering the essential loads, and that inverter has gone back to grid tie. So it's a relatively simple sequence in the scenario of it's open, close, but it's very critical for that open close to be able to happen in a very robust and rigor type of way, because that is the switch now that enables that battery to be that resilient energy source when the power goes out. So let's take a look at our second use case here, because that's the most basic one that I can start with. One that we're seeing a lot in the marketplace is what I call the coexistent scenario, right? So this is two separate buses, two separate power buses with a generator on one and an isolation switch and a battery on the other. So this is one where I see a lot of engineers go, well, I'm tried and true on generators. I understand what that is, and I know how to be able to make that work. But this battery thing is over here, and somebody's asking me to integrate it. So I'm just going to stick it over here on the side, and we'll use it for what it is. So in this scenario, I'm not going to claim any more sustainability or cost avoidance or anything like that, because you're basically going to run two separate independent systems. So let's see what that looks like as we walk through it. So normal operation, we are green coming from utility. Now we signal that power loss, and now that again, that isolation switch says, hey, power's out. I sent a signal to the battery, and that battery's creating power on that one bus. And at the same time, the ATS has started the generator on the other bus and now has transferred the critical load to the generator. Now, in normal, those two things happen simultaneously, but for the purposes of explaining it on a PowerPoint slide, we broke them up in a sequential order. So normally both happen at the same time. So now let's look at the scenario again when the power comes back. So now power's coming back, green line's going to come down through, and as we talked about, the isolation switch is now going to realize, hey, power's back. I'm going to send a signal back to the inverter, say stop making power because I got utility back. So when that power is gone, isolation switch says, great, I'm going to close myself, and I'm going to allow that utility power to flow back into the system and connect that inverter. Same thing on the other side now, where the generator is saying, hey, with the ATS power's back, I'm now going to switch back to utility and shut the generator off. So there's lots of versions that can happen here, open transition, closed transition. We're not getting into those details per se, but this is what it would look like if I was to be able to create two separate independent systems. One side was a generator, one side was an isolation switch, okay? So that's kind of like these two base cases that we've been able to create to help the market understand how to implement a source isolation switch.
All right, so moving on a bit, and so we understand this basic use case now. So let's move into use cases where we see a strong value around battery first, specifically to help optimize sustainability overall. Can you walk us through a couple of examples?
Yeah, yep. So the first thing to note here is going to be that we've created, and we talked about this in one of our podcasts, right? Well, UL has created a new standard that allows that battery to be used in emergency power situations, right? Because that's, we showed you the base case number 2, which we see a lot of and saw a lot of in the beginning, I believe, because there was no governance around how do I use a battery in a, they call it NFPA Article 70 use case, right? Which basically says, hey, you have to have life safety certification, meaning that, and it's not life safety necessarily that's the operating table, somebody's going to die type scenario. It's more of like including like a hotel needs to have a generator that if they had a fire, they could keep the lights on, they have the ventilation system going, people can get out of the building, that kind of stuff. And so if you're going to put a battery in that chain, right, in that equation, that battery and system has to be certified for those standards. And so batteries and their natural form easily get to that point, right? Because they are used in UPSs and things like that today as a standard. What hasn't been has been that isolation switch. So now with this adoption of the new UL standard for the isolation switch, there's an opportunity to use the battery and the generator in the same same series of events, right? So you'll notice in this first case that we're going to look at, we've put the source isolation switch upstream of the ATS. So they're now connected to the same critical load that's downstream. So in this scenario, what you're going to see is we're going to take advantage of the ATS timer being used to delay the generator start. And so the way the ATS timer works is it's going to count to, I believe it's up to 8 seconds before it's going to start. So when it realizes the utility's gone, it's going to go 1 Mississippi, 2 Mississippi, 3 Mississippi. And so it's going to not start because normally power would go out, it would start the generator and it would transfer on over. So let's walk through this scenario now. So the power is going to go away. And when it goes away, again, the source isolation switch is going to open that system, and it's going to send a signal over to the inverter and say, hey, power's gone. I need you to create voltage. So it says, okay, I'm going to create voltage. Meanwhile, the ATS is going 1 Mississippi, 2 Mississippi. Before it gets too far, it goes, oh, power's back, because the inverter from the battery has now created energy and is supplying power to the ATS. So the ATS just thinks it's regular utility and just sits there. Now, let's take the scenario where you've gone to battery first, but the battery is going to expire. So now if we go to the next step, what's going to happen is the power basically goes away as it expires. The ATS goes back to its 1 Mississippi, 2 Mississippi, and this time it hits its timer because power doesn't come back. And that's what then starts the gen, and the gen now provides power to the critical load. So in this scenario, I've gone battery first, expired, now I'm on my generator. So now the generator is going to continue to power the load as long as there's fuel in the generator itself until the utility comes back. So in this scenario, utility is going to come back. The isolation switch, again, is going to recognize that, hey, utility's back when that green line comes back onto the page. And what it's going to do is send a signal back to the DER to say, listen, power is back. Just want to make sure that you're not creating voltage. And when it confirms that, it's then going to close the system, and it's going to provide utility back into the system itself. So if we go to the next one, what you'll see is that power coming back sends the signal to the inverter. Inverter says, oh, I'm not creating power. The isolation switch is okay. I'm going to close. As I close, I provide power back through, which gets to the generator and the ATS. The ATS says, hey, power's back. I now transfer over to utility, tell the generator to shut off. Okay, and now I'm back to a normal situation. So this would be a scenario where, from an engineering perspective, a client who's looking to be more sustainable, a client that's looking to be able to lower costs, this is going to be, how do I take the battery energy storage system and integrate it into a design that provides them both sustainability and resiliency at the same time. So a second version of this, now if we go to the it's kind of like a use case that's got like an A and a B to it. So in this case, all we did is switch the order of the ATS and the isolation switch. So before we were going to the isolation switch first, in this case, we're actually going through the ATS first to the isolation switch. And some of this will be preference in design. Some of this will be maybe the size of the system will dictate a little bit. It might be new construction versus retrofit will also drive a decision here. But the good news is that you can use these interchangeably. It's not like it's got to be one or the other. But in this case, what we're going to do is we're going to use a start inhibitor for the ATS. So in normal operation, what's going to happen here is that the inverter, the battery energy storage system, is going to signal the ATS to prevent it to say, don't start. So if we take this scenario now and we lose power, like we did before, what's going to happen here is, as you see that green line go away, the inverter is going to send that signal to the ATS saying, hold on, wait, wait, wait. And while it's saying, wait, 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 the isolation switch is signaling it to say, hey, go to grid forming, and it's going to create voltage to be able to power the load itself. So this whole time, there's basically a signal being sent to the ATS saying, wait. Now, what will happen will be is that if and when that battery expires, that's feeding the circuit itself, if that expires, then that inhibit signal is going to go away. And when that inhibit signal goes away, the ATS is going to say, oh, I'm going to start the generator, and it's going to go to generator. So if we go to the next one, what it's going to show now is that battery is going to expire, power is going away. The ATS is going to realize it went away because the inhibit signal went away, start the generator, generator provides power, power comes back through that isolation switch that says, hey, I see that power's back, make sure, Mr. Inverter, you're not creating power. I'm not creating power, great, close, and now we're going to provide that power coming from the generator to the load itself. So that's how you put the ATS first and you use the inhibit signal. So if we look at how when normal energy is restored, the green line is going to come back online. The ATS is going to realize, hey, energy's back. I'm going to shut the generator off. I'm going to take power from the utility. The utility is now going to provide power through the isolation switch itself to the load. And I'm back to a normal grid tie type scenario that I started with. So, and again, I can either put the SIS first or I can put the ATS first. And one, I'm going to use the timer, and the second one, I'm going to use the inhibitor. But in both of these scenarios, you'll see it up there on the blue part of the slide, a higher sustainability and resiliency package, because typically if I've got generator on one side and battery over here and they're not connected, I could have generator available, but then my battery expired and I can't get my generator power to where my battery stuff was. And so having separate buses and not connecting them is providing me less resiliency, because ideally when I put the two of them together, if one's available or the other's available, I have the option to be able to use either or. And certainly with them on the same bus, I can take advantage of going battery first and not even starting the generator if it's going to be a somewhat shorter outage, which gives me a higher sustainability option. So key thing to kind of take away with this, kind of to wrap it all up, is going to be is that we aren't going to be able to use the same boilerplate spec that we've had for 20 years in these new scenarios, because these batteries are going to require a different approach than just using transfer switches. And it is a great time for us that as we see these new technologies come into play, for us to be able to update those specifications to take advantage of better sustainability, better resiliency, and providing our customers a better overall solution.
Well, thank you, Russell. That is a fantastic way to bring this all together and wrap it all up. I do appreciate it.
No problem.
Well, thank you so much for your time. This has been a video discussion with Russell Senesac from Schneider Electric and ASCO. And we do appreciate you joining us today. Thank you and goodbye.